Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is gravitational potential energy in general. And just to let you know what we mean by the term in general, we're talking about gravitational potential energy, which you've already learned about, but not in the specific or special case where we are near the surface of Earth. That's a situation that we call a special or specific situation in physics. We're talking about the general case where you could be anywhere around Earth, or for that matter, anywhere around some massive object like a moon of a planet or even a galaxy or a star in space. So therefore, this is the most general treatment of gravitational potential energy, and we're going to need to use some advanced mathematics, actually from calculus here. So it's a bit of a challenge, and it's an interesting topic, but some of the neat things we're going to be able to talk about as we go through this section is the concept of space travel and even some ideas relating to black holes. So if that sort of thing interests you, then I think you're going to enjoy this topic. Take a moment to pause the video and have a look at the specific questions we will answer, as well as where we are in the unit schedule, and also what the learning goals and success criteria are. Okay, please do that now and then return. Okay, and you're back and we are ready to go, so let's get started. First off, let's answer a question. What is wrong with the old EG formula? When I say the old EG formula, of course I'm talking about what you learned in grade 11 and what we also discussed a few chapters back. EG equals mgh and its cousin delta EG, which equals mg delta h. This formula, of course, is talking about the work done when you raise an object up in a gravitational field, or when the gravitational field acts to lower it down, for example. You exert a force equal to the force of gravity, which is mg, and you move at a distance delta h. So this is a force, that is a distance. F times delta d, of course, is work. And we understand that when we are lifting or dropping something, the work done can be described as the change in gravitational potential energy. Okay, very good. Here's the problem. The problem is that the g value in here, and I'll just highlight that with another color, g is equal to 9.8 newtons per kilogram, but only if you stay very close to the surface of Earth. Suppose you want to travel through space. Well, you're going to have to lift something like a satellite or a space capsule with you in it, much higher than the surface. As you know from the previous video, it's in section 6.1, as you go higher and higher, g gets less and less. So how is this formula going to work if one of the supposed constants in it is actually changing? Well, we need a new formula. So what are we going to use instead? Here are some images taken from your book. The book is Physics 12 by Nelson, and this is in section 6.3. Here's a graph that I imagine you're familiar with. It's the force of gravity. I'll just put in a little g there. The force of gravity as a function of distance from the center, so this would be the letter r, the distance separating any two masses. And this, of course, comes from our good friend Fg equals g times big M times little m over the distance squared. So as r increases, of course, the curve falls off like this. Now, this is a force distance graph, which means that the area shaded in blue here represents the work done to go from a position called R1 away from some object to another position, R2. So this R1 to R2 is kind of like the delta H in the old formula. And the mg, which is the force that I mentioned here, we now see begins to diminish. So since we realize we can't use the old formula in this situation where the force changes so much that it's not constant, therefore what are we going to do? Well, we can use the old idea that on a force versus distance graph, or in this case force versus r, the work done is the area beneath the curve. Now, this is a difficult area to calculate. It's got a curvy top. So how would you do it? You could estimate the area by sort of dividing this area into many different rectangles, for example. But that wouldn't be very accurate. It would be very time-consuming. So what we actually have to do is use calculus. This is actually one of the things you do in calculus, is you learn how to calculate areas beneath challenging curves like this. Now, since calculus is not a prerequisite for this course, I can't expect you to go learn calculus, although some of your university professors are going to assume that you know certain things, and they're just going to tell you to go figure it out yourself. So just a little warning there. What are we going to do? We're going to borrow the result from calculus for the area beneath here. So are you ready for it? I'll just switch back to another color here. Here's what the area comes out to, and it's a little bit of a weird, wacky formula, but I'll give it to you anyway. It's negative g big M little m. So these are the masses of the two objects that are being separated. One might be, let's say, a planet, and one might be, let's say, a spaceship. So negative g big M little m over R2, the final position over here, minus negative g m big M little m over R1. Now pause the video for a moment and look at this and try to digest it if you need to, and then come back. All right, now that you've had a chance to look at this, you're probably wondering a couple things. First of all, why put two negatives in here when I could just write this as a positive? That's a question mark that you might be wondering. Well, let me just delete what I just drew in there. The reason for that you'll see in a moment, but if you really want to see how we get to this part, take a look in your textbook in section 6.3. You may have to go through the derivation several times to understand how they did it, but it's well worth your time. Having said that, the reason I want to do this is because, as I mentioned, the area is going to be the same as the work done, which is also the same as the delta Eg. So look what this gets me. It gets me delta Eg equals negative g big M little m over the final distance minus negative g big M little m over the initial, or the starting distance. And what do we get now? Well, delta always means final minus initial. Anytime you see delta, you automatically think final minus initial. So this is actually Eg final. Here's this minus, and this is Eg initial, or Eg1. Look what's happened here by writing this in the weird way that I did. Negative GMM over R2, actually. Sorry, I can highlight that over here. Negative GMM over R2 is associated with Eg final. Negative GMM over R1 is associated with Eg initial. And the minus sign over here is actually this minus sign there. So what have we figured out or borrowed from calculus? We've borrowed the idea that the new Eg is not mgh. That's old, that's done. The new Eg has a negative in front of it. It's got the universal gravitational constant. It's got a big M for, let's say, the planet that you're trying to move away from. It's got a little m for your mass, like the mass of a spaceship, over the distance that you are, the two centers of those two objects are separated. And here is your new formula for Eg. It's a little bit tricky, it looks a little weird, it looks nothing like what we had over here, but it actually comes from calculus, and if you work out the units, you'll see you do get joules on the left-hand side here when you plug in all the right units on the, you'll get joules on the left side if you plug in all the right units on the right side. Okay, so pause the video now and think back about what I've discussed. Look in your book if you have to. It's well worth your time to just kind of digest this. This does not always come easily. Okay, and you're back. And a few more words about this. What we call this is the gravitational potential energy of a system. And when I say of a system, what do I mean? I mean a system of two masses. So any two masses, by virtue of the fact that they are separated by a certain distance, and because they have mass, they automatically have what's called gravitational potential energy. And you know this is the case. If you want, stand up on a chair and realize that you, with mass little m, and the Earth with mass big M, separated by a certain distance, there is gravitational potential energy there. You could jump off the chair and pick up kinetic energy. Work will be done on you. So there is a link here between work and energy. All right, moving right along, what we can do is take this formula here and we can graph it. And that's what this other graph here, which is also from your textbook, shows you it's a graph of EG versus R. Now, one thing to notice, the graph starts from way down here. It's below the axis, the R axis. Why is that? First of all, notice that EG is always negative. You cannot get a positive number for EG. And this is strange because in the past with the old formula, you were able to get a positive number. You just had to be above height equals 0. Well, here you can never get a negative number out of this formula. Mathematically, it's not possible. To get a positive number, rather. So what does this mean? Another thing, as the denominator increases, in other words, as the two objects move farther and farther apart, the denominator grows, and therefore the overall fraction gets closer to 0. So this is described by a graph that rises up from below and comes up, never to cross the r-axis, but to always get closer and closer to 0. For those of you who've taken advanced functions or calculus, you know that you can write a limit as r approaches infinity of the EG formula that is equal to 0, as shown by this graph. And if you haven't taken calculus or advanced functions, don't worry, just understand that this is the shape of the graph based on this function. It's kind of like a y equals negative 1 over x function would behave. Okay? So why do I want you to pay attention to this? Because it's going to help you understand the idea that as an object moves farther and farther away from a planet, let's say, its gravitational potential energy gets less and less negative. It climbs up towards 0. It's almost as if you are stuck at the bottom of a well and you're trying to climb your way out in order to escape. If you could just get up to 0, you would escape. Of course, the only way to get to 0 is to keep going farther and farther away, and this of course relates to the idea that that the force of gravity is infinite. It spreads out all through the universe. There is no place where the gravitational force due to any object actually becomes 0. It comes close to 0, but it never actually gets to 0. Gravity is a force with infinite reach. All right, so there's a little bit of the background. Enough of the theory. Let's actually try to use this. Let's take a question also from the same book where they ask you to calculate the change in gravitational potential energy for a 1 kilogram mass lifted 100 kilometers above the surface of the Earth. And they ask you what percentage error would you have made if you used the old formula as opposed to the new one. So what I'd like you to do is pause the video and try this. I'd like you to take a 1 kilogram mass. This is going to be m equal to 1 kilogram. And since we're lifting it above Earth, you got to think of the other mass, capital M, as the Earth's mass, which is around 6 by 10 to the 24 kilograms. Okay? Now, in the old method, what you would do is you would say, okay, well, I'm lifting this up 100 kilometers, so you would put in delta H equals 100 kilometers, and of course you'd convert that to meters, so what's that going to be? It's going to be 10 to the 5 meters, and you would just do delta EG equals mg delta H. You'd plug in your 1 kilogram, you'd plug in your 9.8, you'd plug in your 10 to the 5, and what would you get? Well, you'd get 9.8 by 10 to the 5. That wasn't too hard to do. Joules, of course. But let's see what you get when you use the formula that we just, quote, borrowed from calculus here. Negative GMM over R2 minus negative GMM over R1, subtracting the two gravitational potential energies. So here we go. You're going to write delta EG, and this, by the way, is the new way. You're going to write negative GMM over R2 minus negative GMM over R1. But what are you going to use for your R2 and your R1? Well, remember, now the R2 and the R1, they refer to the distance between the centers of the two objects. So if you try to imagine that what we're basically doing is going from the surface of Earth, which has a radius of something like 6,380 kilometers, they say in your textbook, and we're going up, up, up a little bit higher to a final position, which from the center is now 6,380 kilometers plus the 100 kilometers that we raised this object. What happens now is you've got 6,480 kilometers. Of course, don't forget, you have to convert to meters all the time, right? So what are you going to do here? You're going to plug in for R2 the final value of 6480 and tack on 3 zeros. 6380 is going to go in for your first value. The mass of 1 kilogram is still needed. That's little m, the object you are lifting. And of course, big M is going to be the mass of Earth, which we wrote over here, 6 times 10 to the 24 kilos. So what I'd like you to do now is pause the video, sub these numbers in. Be very, very careful with order of operations. There's a lot of places to make mistakes here. You're also dealing with a lot of scientific notation. So I recommend you calculate the first value separately, maybe write it down, then calculate the second value. They're both going to be negative, then subtract them and see what you get. You should get a number very, very close to this. And what I'm going to do is pause the recording here for a moment, and I'm going to calculate this as well, and then we're going to both compare. Let's do that now. Go. Okay, folks, I'm back here. I've done the calculation. I hope you have too. And let's see what numbers we got. I'll just go back to blue here so we can follow along. I got 968013, and then a bunch of digits after the decimal. They're not really important. This is the number of joules that I got. What do you notice when you compare with the original using the old formula? Well, you can see, first of all, that it's less. Now, why would that be? See if you can figure out why the number using the new formula would actually be less. Pause the video and think about that for a minute. Okay, you're back, and hopefully you've thought of it. Maybe you came up with the answer. The reason is this formula takes into account the fact that as you lift that object 100 kilometers, the value of little g that we would have used in the old formula, that's diminishing. So actually the work done will be less, and therefore we would expect this number to be a little bit less. Now it's not much less. After all, you're only going 100 kilometers above the surface, which in percentage terms is very, very little compared to the radius of the planet. All right, so there's a little bit of commentary there. You got to see how to use the new formula, and you got to see it compared to the old. And you see there's not much difference for even a 100 kilometer lifting of an object. The problem is when we do space travel, we have to be very exact. And if we lift up more than just a little bit, like 100 kilometers, then obviously there's going to be a bigger difference between these two numbers, and therefore it becomes crucial that we use the new formula. By the way, if you're wondering how accurate this formula really is, keep in mind that all space travel is done basically using Newtonian physics, which is what we're doing right here. So if they, and by they I guess I mean all of the engineers and astronauts and whatnot, can land on other planets with people in the case of the moon, or robot explorers in the case of many other planets and moons of other planets, then they must be doing something right. Well, they're actually using this formula, believe it or not. All right, moving on. So here's a concept for you, which I think you'll find interesting. It's the concept called escape speed. And what do we mean when we talk about escape speed? We mean that we're actually going to try to escape from the gravitational clutches of a planet or a moon or whatever, let's say Earth. We're also going to learn about a related concept, which is the zero or reference point for EG. And when we talk about that, you'll remember that we've actually talked about this in previous lessons when we talked about the old formula of EG. But anyway, I digress. Back to escape speed. What do I mean by escape speed? I mean, let's say you wanted to go from Earth to, let's say, somewhere else in the universe, perhaps the moon. Perhaps you want to travel to Mars sometime in the future. Well, you're going to have to get your spaceship going fast enough around the surface of Earth so that it actually escapes the gravitational clutches of Earth. Now remember, you can't ever truly escape Earth's gravitational field. It's an infinite field in that it extends infinitely through space, but you can get far enough away that you can probably fall into the gravitational clutches of another planet and therefore get to where you want to go. How does this work? Well, first to understand this, we have to go all the way back to this graph over here. The idea that if you are sitting on the surface of a planet, and let's say on this graph that is represented by R1. Whoops. Let's just pretend that R1 represents the surface. And you want to escape. Well, to escape means to get to a position infinitely far away. So we want to go from R1 of whatever value R1 is at the surface. In the case of Earth, that's 6,380 kilometers. We want to get from there to an R value of infinity. So let's go back to the formula and see how that's going to play out. Okay, I've started this. Let's use it. Black there. Okay, there we go. So what is our delta Eg going to be? Well, we can say delta Eg will be Eg final minus Eg initial, which of course, as we've seen, is negative Gm1, or sorry, big M, little m is what we've been using, over R2 minus negative Gmm over R1. And as we just discussed a moment ago, the idea of escape means that R2 is going to equal infinity. So what does that mean for this part of the formula? Well, the denominator is going to be huge, and therefore negative some number over a huge number is going to make all of this equal to 0. So the delta Eg is going to be negative G, big M, little m, over R1, where, if you recall, R1 is going to be the radius of the planet, because I'm assuming you're starting off at the surface. Most spaceships, when they take off, are on the surface, so this is a reasonable number to put in. So now we know what our delta Eg is. We're going to have to do work on some space capsule to raise it up to infinity. Now question, where does that work come from? Well, the answer is you have to exert forces by igniting the engines, and so you're going to do work that way. You're going to exert a force through a distance, and we're going to get the spaceship moving. We're going to give it kinetic energy. So what do we do next? We can say the following. E kinetic has to be converted to this Eg. And in the language that we use in physics, we do the following. We write E total is a combination of Eg plus Ek. All right? And we realize that from the law of conservation of energy, we're going to get that E total at R1 has to be equal to E total at R2. Now, what are the total energies at R1? Well, we have to have kinetic energy. This is where we're going to give that one mighty blast to the rocket and hope that it gets going fast enough that it can escape. And we, of course, will have gravitational energy at the bottom, at position 1, and we're going to hope to convert that into Ek when we get to infinity, plus Eg at infinity. Now, looking back, let's have a look at this. There's going to be lots of Ek, for sure, for sure. How much Eg will we have at the surface? Well, if you think back to what we discussed over here, we learned about a concept called the gravitational potential energy of the system. Any two masses separated by some distance r, we can write that the Eg is negative Gmm over r. So let's go do that now. And in here, that's what we'll sub in. So I'm going to start writing this over here. Ek, which you know, is a half mv squared when we launch, mv1, let's call it. plus an Eg value which is negative, G big M little m, over R1. And now that's supposed to be equal to however much Ek we have at the end of our voyage and however much Eg we have at the end of that voyage. Well, one thing I can tell you, which we already discussed, is the Eg at the end of that voyage when you get to infinity will be 0 because we will be infinitely far away. And now here's where things get a little bit tricky. Got to pull a little bit of thinking out of. We got to do a little bit of thinking here to solve this problem. What is our kinetic energy when we get to where we're going? Well, at the very least, we have to kind of have just run out of speed, if you will, or kinetic energy. In other words, the minimum kinetic energy you can have if you're truly going to escape would be 0. It would be nice if you had more kinetic energy when you got to where you were going, but it's not necessary. To escape, it's kind of like a runner finishing a marathon. All you need at the end of that marathon is the last bit of energy in your body, and then you can collapse and stop when you cross the finish line. So we're going to talk about that minimum energy by saying, let this be 0. And if that's the case, we will have these two numbers equaling 0 plus 0, which of course is 0. And so what's that going to give us? Well, let's bring our Eg across to the other side so it won't be negative. We'll have a half m v1, in other words, the launch speed squared, equals, this becomes positive, gmm over r1. And now let's do a little bit of canceling. Interestingly, the mass of the spaceship cancels out. It doesn't matter what the mass is. The speed is going to be as follows. v1, the speed you need when you launch or shortly after launch, is going to be 2 times the gravitational constant times the mass of the planet divided by its radius, which was r1, and we have to take a square root because we had v squared there. And this is the formula. This gives you the escape speed, the speed something needs to be moving at the surface or very near the surface of the planet in order to get infinitely far away, where Eg is 0, and also, like the marathon runner, basically just collapse and have no speed at the end. Of course, if we could give it more energy and it could be going faster when it got to where it was going, great. We'd be able to cruise around and enjoy ourselves. But to escape, this is the minimum. So I'm going to take this formula now and I'm going to just drag it or just highlight it and then rewrite it over here as follows. V escape equals the square root of 2 times the gravitational constant times the mass of the planet divided by its radius. And you, of course, have to take the square root of that. This is the formula for escape speed. And if you are listening to this and you're in my class, of course, when you look on the equation sheet, you'll see this is not on the equation sheet, which means you do have to learn how to derive it. You've got to use your thinking skills to understand a few things. What are those things? First, the idea that when we get to infinity, that's what it means to escape. Secondly, Eg will be 0 at infinity. And by the way, remember I said we were going to learn a related concept. The related concept is that the reference point for Eg being 0 is at infinity. Remember back in grade 11 when we studied the old version of the formula for Eg, where was the reference point? It was wherever you wanted to make h equals 0, usually on the surface of the planet. However, now there's a new reference point, and that is at infinity, where this formula is equal to 0. Anyhow, continuing on with what you need to know in order to derive this formula, you need to know this, you need to know this, and you also have to think like the runner of a marathon, that the minimum energy we need, and therefore the minimum speed, would be to have whatever speed gets you to have 0 at the end of the marathon. All right, so remember that and you'll be able to derive this formula on a test or wherever you happen to need it. All right, what I'd like you to do now is pause the video and sub in the values of g, mass of Earth, and radius of Earth to calculate the escape speed. Please do that now and then come back and see what you get. All right, and you're back. And if you did this correctly, you should have v escape for Earth is approximately 11 kilometers per second. Notice I'm in kilometers here. You probably calculated it in meters, so be sure to convert that. 11 kilometers per second is how fast something has to be going, which is very fast. You could cross a city in about a second or two going at that speed. That's how fast you got to be going to continue on and get infinitely far away from Earth. Compare this to something we studied a while back when we did orbits going around Earth. Do you remember the orbital speed for a low Earth orbiting satellite? It was around 8 kilometers a second. And so this also makes sense. 8 kilometers per second is not fast enough to escape Earth's gravity. You might end up in orbit. But 11 will get you out. All right? And here's a really extra super cool, neat concept, which is called black holes. Let's see how this relates to the concept of escape speed. And by the way, this is going to be, as you see hidden here, the fact of the day. What is a black hole? Well, if you think you know what a black hole is, maybe you've heard about it in science fiction, maybe you've studied physics and you know, well, I'm going to tell you. When a star, for example, like our sun, or any star out there, runs out of fuel, what ends up happening is the intense gravity of the star causes it to collapse inward on itself. So we might draw a little diagram like this. The star has intense gravitational forces pulling inward on it, and when it runs out of fuel, it has nothing to produce pressure inside to counteract these gravitational forces. And so the star actually begins to shrink when it runs out of fuel to counteract these gravitational forces. If the star is massive enough to generate enough gravitational force, it actually can't support itself at all, and it can collapse into a very, very tiny object that we call a black hole. Now, as you know, when mass gets concentrated into a very small region of space, this formula tells us that we are going to have a lot of gravitational force. This is the FG, the force formula, by the way, not the energy formula. If we got a lot of mass in a really small space, going to have a lot of force. That means the gravitational field is going to be very strong. In fact, if you look over at our formula for the escape speed, it might actually mean that you've got so much mass in such a small region that the escape speed will be way more than what it is for Earth. It could get so high it could actually be equal to or greater than the speed of light. So think about that for a sec. Imagine if the escape speed was greater than or equal to c, where of course c is 3 times 10 to the 8 meters per second. What would happen if this was the case? Well, certainly you would never be able to escape from the surface of this thing called a black hole. You would have to be going at the speed of light, and of course, as we've learned in the past, this is simply not possible. Well, there's other interesting things that would happen. Never mind you not being able to escape from it, but light itself, which travels at, of course, the speed of light, wouldn't be able to escape. So you'd be dealing with a region of space where the escape speed was equal to or greater than the speed of light, and therefore no light would escape. It would be, well, in the words of astronomers, black, and therefore the term black hole. And this is the fact of the day, the idea that a black hole is a region of space where the escape speed is greater than or equal to the speed of light. So what I'd like you to do is pause the video now and do, well, not now, listen to what I have to say. Pause the video in a moment and sub in the following. Take the escape speed formula up here and put in c, 3 times 10 to the 8. I also want you to put in not the mass of a planet, because you actually need the mass more like a star, something with enough mass to generate the intense gravity that I talked about down here to crush it down to such a tiny size that the escape speed goes really high. So let's imagine a star. Let's imagine a star that is, let's say, 5 times the mass of our sun. So what I'd like you to do is look up the mass of our sun, multiply it by 5, and sub that in here. And then I'd like you to solve for r. And what you'll be doing is calculating the distance from the center of this collapsed star at which the escape speed is equal to the speed of light. And therefore, you'll be calculating the effective size of a black hole formed by a 5 solar mass, or a 5 times the mass of the sun, black hole. Take a moment and do that now. I'm going to do the same thing and we'll compare our answers. Okay folks, so here I am back. I've done the calculation, and as it turns out, if you take the equation that we had going into this discussion of escape speed and you just isolate for r, then what will you find? So I'm working with this right here, and if I take this down here, I have r equals, and I have 2gm over the escape speed squared, and we're going to put in c squared because this escape speed is the speed of light for a black hole. What I get for a 5 times the mass of the sun, or a 5 solar mass black hole, is the following number. Now, you may have slightly different digits here at the end. What I'm using for the mass of the sun, just in case you want to be completely in step with me here, I'm using 2 times 10 to, 2 times 10 to the 30, not 2 times 30, as the number of kilograms. Okay, and if you sub that in and you do 5 times that number, don't forget to multiply by 5, then upon substituting in, you get about 14 or 15,000 meters, which is, let's just call this 15 kilometers. Now, are you surprised that an object, a star, 5 times as massive as our sun, if it collapses due to its own gravitational forces, will become a black hole, and the distance from the center at which the speed of light is the escape speed is just 15 kilometers. Does that surprise you that this black hole is so tiny? Well, I was surprised the first time I saw this kind of calculation. We tend to think of black holes as these enormous objects roving through space, just destroying and capturing everything in their path. It's actually not the case. Black holes are quite small if they are on the order of the size of a star. There are things called supermassive black holes. These exist at the centers of galaxies, and they may be millions of times the mass of our sun. So of course you'd have to sub in a number much greater than 5 times the sun's mass. But even then, these black holes might not be as big as you thought they would be. Just an extra little bit about the black hole. Once it does collapse, because nothing can stop the gravitational collapse, the actual remains of the star are just a tiny point at the center, and we have a name for this. We call it a singularity. It's a point of literally 0 size. It's a mathematical point in which all of this mass is concentrated. So sometimes we say it has infinite density. And if you imagine this 15 kilometer radius around it, so let's try to draw this. Let's draw this radius as 15 kilometers here. This is the radius within which the escape speed is equal to or greater than the speed of light. And so we call this the Schwarzschild radius, named after the famous astronomer or theoretical astronomer who came up with this idea. And of course, the point at the center is called the singularity. The region or the boundary, the sphere defined by the Schwarzschild radius is called the event horizon. And if you've ever heard the name event horizon, as the name suggests, once you cross the event horizon, I guess that's the last event that we're ever going to know about from you, because if you ever went into a black hole and you kind of had the thought of, oh, well, I'll sacrifice myself, I'll go into this black hole, and I'll just radio back to my friends on Earth or from a spaceship nearby what it's like inside this black hole. Sorry, that's not possible. How would you send the information out? Would you radio using your cell phone, which uses microwaves? Sorry, they are examples of light. They travel at the speed of light. They can't escape. Would you use Morse code, flashing a flashlight, to send signals? Once again, sorry, the light from your flashlight will not escape the black hole. So once you cross the event horizon defined by this sphere that goes around the black hole in 3 dimensions, there is no communication allowed anymore with the outside universe. You are stuck forever inside there, and you're probably dead. So don't go too close to a black hole. But good news, the distance from the center of the black hole, after which you can never escape, is not very large, even for a 5 solar mass black hole. All right, so moving on. Let's see what else we've got here. We've been talking about the idea of gravitational potential energy in general and how it relates to kinetic energy and the concept of escape speed. And so now it's time to look at these two types of energy as they relate to one another on a special kind of graph. It's an energy versus distance graph, which you've already seen. The first time you saw this was back here, don't forget. And the idea of these three graphs, which are also from your textbook, Physics 12 by Nelson, the idea here is as follows. Let's take a look at this graph, the first one, case number 1, where the total energy equals 0. This was the idea that we worked on when we talked about escape speed. We talked about how the total energy in a system would be the gravitational plus kinetic, and we realized that if you're to just barely escape, this means that when you get to infinitely far away, you'll have zero kinetic energy left, just like that marathon runner. So we realized that the total energy is coming out to 0, and so now let's graph this so we get another representation. As you move towards infinity, your gravitational potential energy increases, but from a negative value. So it rises up towards 0, but it never reaches 0, and it never crosses the r-axis. As you're rising, moving away from some object, it's like a ball being thrown up. You're slowing down. Throw a ball in the air, watch it slow down. As its gravitational potential energy increases, it's going to lose kinetic energy. And that's what this top graph is showing you. In the special case of an object having just the right speed to just barely escape, the total energy is 0, so these two graphs must add to 0, which means they're going to be a mirror reflection of one another in the r-axis, and they will be centered on the r-axis, and therefore at any given time the negative value that Eg has at a certain distance from the center added to the positive Ek value. Remember, Ek values are always positive. They're always greater than or equal to 0. You can't have negative Ek because of the v squared term. These two are always going to add to 0. And so this is a graph of what it would look like to have just the right speed and energy to escape, but not have any energy left when you get there, to wherever you're going. Total energy 0. What would it mean if you had greater than 0 total energy? Well, as you might guess, this means you will escape and you'll have some speed left over when you get there. You'll be like a marathon runner who actually still has some energy to walk around and maybe sign some autographs or just hang out with friends. As you approach infinity, your Eg, of course, approaches 0 from below, as we saw before. Your Ek comes down like a ball being thrown up away from the ground. However, the Ek never reaches 0. It levels off at a value that's equal to whatever your total energy was. So this is ideally what we would want in space travel, because we don't just want to escape from Earth. We want to actually have some energy left over to maneuver and do stuff when we get to wherever we're going. Let's look at the third case, which is ET, total energy less than 0. Here, your Eg increases, but because you weren't launched with enough speed, your Ek hits 0 before you escape, which means you are bound to Earth. A total energy that is negative less than 0 is associated with an object being stuck to Earth. Guess what, folks? You and I and everything around you that is sitting on Earth and is going to be sitting on Earth for the foreseeable future has a total energy less than 0. Even if we get something moving, even if we fire a bullet up in the air and give it lots of Ek, the gun is probably not powerful enough to give it enough Ek to overcome or to allow it to climb out of the potential well. Remember, we used that term when we were talking about this graph the first time. It's as if you're stuck in a well and you're trying to climb out. You need enough Ek to get to 0, to get back to ground level. Not going to happen in most cases. You need a very powerful gun or a rocket in order for that to happen. So that's what these graphs look like, and they are just a visual representation of all the concepts we've been discussing. And so we're going to finish off with a special case involving all of this new Eg business. It's a case where an object is in a circular orbit around a planet, let's say. And of course, if you think back to what we just discussed, being in an orbit means you are not escaping, so you're in this situation. You are bound to Earth, not on the surface, mind you, more like the astronauts in the International Space Station who are orbiting around Earth. They're still bound. They're a little bit higher, and they're moving a whole lot faster than you and I are right now, but they are not going to escape on their current orbit. So that's what we're dealing with here. What happens when we are in a circular orbit? Well, I need you to think back to what we discussed a long time ago when we talked about uniform circular motion. What do you remember about uniform circular motion, UCM? Well, one thing was we could write that Fc was equal to mv squared over r. I want you to keep that in mind because we're going to need to borrow it in a moment. Now, let's think back to, in this video, what we've been discussing in terms of energy. The total energy when you're moving around in space is a combination of your gravitational potential energy and your kinetic energy. And we have formulas that we can substitute in here. Eg is always equal to negative g big M little m over some distance from the center of these, separating the centers of these two objects. Your kinetic energy is always a half of your mass, little m, v squared. Now, we also know that if you are in uniform circular motion, this is only if you are in uniform circular motion, then we can write that the force is mv squared over r. Well, guess what? If you take a look at part of this formula, specifically this part here, the mv squared, what are you going to notice? Well, in here is an mv squared, right? And so there's going to be a substitution that's going to happen because we're in circular orbit. We're going to be able to do something really neat here in just a moment. What is it that we are going to do? Well, first thing we're going to, sorry, folks, just hold on one sec, got it paused. Sorry about that, folks, I'm back. Okay, so here's what we are going to do. We are going to take the circular motion force formula, which of course is mv squared over r, and we're going to realize that if we are in a circular orbit, for example, around a planet, of course we're talking about space travel here, so this would make sense, planet mass m, then we can write the following. The centripetal force is equal to the gravitational force. You learned this back in chapter 3 when we talked about circular orbits the first time. So we can write that mv squared over r is equal to big G, big M, little m, over r squared. Notice this is not the energy formula, this is the force formula. There's no negative sign, like there is over here, and there's squaring of r, unlike over here in the Eg formula. Don't get these two mixed up, they're very different things. Anyway, I digress. Let's go back and see what we got here. mv squared over r and gmm over r squared, look, one of these r's cancels with one of those. Now, the m cancels as well, the little m, but I'm going to leave that because remember what I pointed out to you a moment ago, the mv squared over here and the mv squared over there look the same, and I want to use that for a substitution. So what am I going to do? Here is an mv squared, which is equal to that. That's what I'm going to sub in. And what am I going to get here? From my E total formula, I'll have negative gmm over r plus a half of whatever I sub in for mv squared, which from this is gmm over r. Now, why do I want to do this? You're going to see in a second. What does this give me? Negative gmm over r plus a half of gmm over r. Well, if you have negative 1 of something, and then add a half of that same something, you end up with what? Negative a half of that thing. So what am I going to do right now? Allow me to do the following. Let me get rid of that negative over there and just stick it in here. Why do I want to do that? And yes, this is legal. I'm just moving the negative sign around in a multiplication. Why do I want to do that? Because negative gmm over r is our good friend Eg. And if I do this, look what I have derived. 1/2 of Eg. In other words, I've developed or derived an important result that deals with circular orbits caused by gravity. It's that the total energy, where can I write this here? Maybe down here. E total in a circular orbit is equal to 1/2 of whatever the gravitational energy is. So if you know the gravitational energy at some point in circular orbit, then you automatically know the total energy. And remember, E total is equal to Eg plus Ek. So we're going to end up using these two ideas to solve some problems involving circular orbits in a really neat, easy, quick way. Let's take a look at an example. This is the last part of the video. Let's see what we got. This question is also from your book, by the way. What is the total energy needed to place a 2,000 kilogram satellite into circular Earth orbit at an altitude of 500 kilometers? So, first of all, let's draw the situation so that we have some sort of idea what's going on. Here's Earth, and we can denote its radius with this line, and we can also denote the location of the satellite, which is going around in a circular orbit at 500 kilometers up. So here's 6380 kilometers, and here is an additional 500 kilometers. And we know the mass of the Earth is, let's just call it 6 times 10 to the 24 kilos, to keep things simple, and the mass of the satellite, little m, is 2 by 10 to the 3 kilograms. Now, a couple of things we know. We are in a circular orbit, so we have not just launched something straight up, allowing it to fall back down. We've launched it the way NASA launches their space shuttles, or used to launch their space shuttles. They do it sort of on an angle so that the spaceship ends up going around the Earth instead of just straight up. What can we write? Well, at 500 kilometers above the surface, the first thing I can do is write the EG. EG is always negative GMM over your distance from the center. And so if I plug in the numbers, I have negative G times big M, mass of Earth, little m, mass of satellite, over the distance from the center, and this will be the 6380 kilometers plus the 500 to give me 6880 kilometers, but I got to get that into meters. Be careful, don't square. This is not the force formula, it's the energy formula. And what do you get? I'm just going to pause my video here while I do a calculation. Okay, folks, and sorry for the delay there, the little pause. I get the following number. Negative 1.163 by 10 to the 11 joules of energy. So that's the gravitational energy of a satellite that is a mass 2,000 kilograms when 500 kilometers above the surface. Now, because it's a circular orbit, I can use this special result here that E total equals half EG. So let me do that. We don't have to calculate too much here. We just have to sub in this number. We already know EG, negative 1.163 times 10 to the 11 joules, and that's going to give us a number. I'll just take this on my calculator, divide by 2, and what do I get? Check that you got the following number. Still negative. Whoops, I forgot the negative in there. So negative 5.816 times 10 to the 10 joules. Notice how my total energy is negative. And if you're in a circular orbit, that means you aren't escaping. You are bound to the Earth. That's this case here. All right? Things are hopefully starting to make sense. So there's our total energy. Now what else do I know? I know that EK plus EG are equal to E total. And so what can I do with this? Since I know E total, which is this number, and since I know EG, which is that number, I can solve for EK. I get the following. This is the equation that I get. And if I solve for EK, oops, what am I going to get? You can pause the video if you want and calculate this using your calculator, or you can simply realize that it's actually going to be the negative of this, so it's going to be positive 5.816 times 10 to the 10 joules. See if I can fit that in there. From this information, what can I get? Well, since I know that EK is equal to 1/2 mv squared, then I can do the following. 1/2 of the mass of the satellite, which is 2,000 kilograms, times its speed squared is equal to this number. And so now I can solve for v. At this point I will pause the video and do that, so hang on. Okay, and what did I get here? I came out with a number of 7.627 meters per second. And does this number look familiar? Around 8,000 meters per second? Yes, it does. In an earlier video on uniform circular motion and gravitational orbits, we learned that a low Earth orbiting satellite moves at about this speed. So hey, guess what? The energy ideas work. So does the force idea that we learned in Chapter 3. Now, all of this is neat. However, I haven't really answered the question here. It asks, what is the total energy needed to place this satellite into circular Earth orbit? So how are we going to actually answer this? Well, to answer this, I actually need a new screen. So here's what I'm going to do. I'm going to do a little cut and paste job here, if you don't mind. Going to take all of this. I am going to copy, and I'm going to bid farewell to my very first screen. This has never been done before, guys. Don't try this at home. I'm going to paste that in there. Amazing what you can do with technology. All right. So here is what we just did. And now, while I've shown you a lot of stuff that you don't technically need to do in this question, I would like to show you what you do need to do. And by the way, I didn't waste time here. You will need to do these calculations for other questions. I just wanted to show you that in here. All right, so what is the total energy needed to place the satellite into this orbit? So here's the first thing we got to do. First of all, we got to visualize the problem. We start with a satellite on the launch pad on Earth. So let's imagine that we're starting off here. And we're going to move up to an altitude of 500 kilometers right there. Now, let's look at what's going on the surface. On the surface, you are stuck. You have an EG, which is negative. It's GMM over whatever distance you are from the surface. This is going to be, and you can calculate this yourself, negative 6.67 by 10 to the negative 11. Multiply that by the mass of Earth, 6 times 10 to the 24. Multiply that by the 2,000 kilos, which is your satellite mass, and realize that here you are on the surface. That's 6380000 meters. Take a moment to calculate that. I will do. Okay, folks, I'm back. I've done the calculation here. The number that I'm getting is negative 1.125. Sorry, not 125, but negative 1.255 with a few other digits in there, times 10 to the 11 joules. Now, let's just check if this makes sense. EG, way up in orbit at 500 kilometers, was negative 1.163 by 10 to the 11. On the surface, the number is more negative. It's 1.255 by 10 to the 11. Does that make sense? Yes, it makes sense. The closer you are to the center of the planet, the further down in that potential well you will be. So we know that we started with this much energy, and we were not moving. When you're on the launch pad, your speed is 0, and therefore your EK is 0, which means that on the surface, your total energy, remember you're not in orbit, so don't use the half EG idea. Don't say this when you're sitting on the launch pad. That's nonsense. If you're sitting on the launch pad, you're not in orbit. If you're sitting on the launch pad, total energy, which is EK plus EG, is going to be 0 plus this negative number that I just calculated, negative 1.255 times 10 to the 11, which is pretty easy. That's just going to give us this. So that's the total energy we have on the surface. But I want to get up to a place in orbit where I'm going to have a lot higher energy, as in a less negative energy. What do I have to do to get into orbit? Well, I'm going to show you this in a different color so that you can keep everything straight. In orbit, I'm going to need EK. How much EK do I need? Well, you already calculated that answer. It's right here. I've got to get myself this much EK. So in answer to the question, what total energy is needed to get me into orbit? At least this much, because I got to be moving. I got to have EK to be in orbit. But what else do you need? You also need to increase your EG. You need a delta EG. We got to do work on this satellite to get it up to the orbital height. How do we do that? Well, we realize that in the beginning we had this much EG, and at the end we're going to have this much EG. So I want to go from an initial value of this to a final value of that. What's the change? Easy, just subtract. Change is delta, is subtraction. EG2 minus EG1, that's going to be this number, negative 1.163 by 10 to the 11, minus negative 1.255 times 10 to the 11. And if you calculate this, what do you get? Give me a moment to pause, and then I'll let you know. Okay, and I'm back. What number did I get here? I got the following, 915. Let's see if I count digits here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9.155 times 10 to the 9 joules. I got to gain some EG. So in the end, how much total energy do I need to get into orbit? Well, I've got to, let's see what color I can use here. I've got to get this much EK, and I've got to gain that much EG. Add these up, and you will know how much total energy is needed to get up into orbit. So here we go. Let me just add that, 5.816 by 10 to the 10. And the answer I get is 6.7 times 10 to the 10 joules of energy needed. That's a lot of energy. That is 67 billion joules. Where are you going to get that kind of energy with a really large rocket burning a lot of fuel? It is not easy to get a 2,000 kilogram satellite into orbit. So, where are we now? We've spent a long time. This is probably one of the trickier concepts in the entire course, which is why it takes time. It's also pretty much a double lesson. It takes a couple days to do this. So think of this hour-long video as more like 2 30-minute videos. We've covered a lot of ground. We've talked about energy in some strange ways, made more complicated by strange formulas, one of which is always negative, which also complicates things. However, if you take time to think about what I've said, and if you pause the video and rewind as needed, I hope you'll be able to make sense of this. I got to let you know, when I did this in first year university, I was even baffled. It's only after I really sat down and thought about it for as long as I could that it really started to make a bit more sense. Hopefully you'll arrive somewhere in the middle and be able to get some understanding. But I leave you with that now. I hope some of it has made sense once again. I hope you've enjoyed the discussion of black holes. Thanks for watching, and I'll see you in class. Have a good day.